A recent study by researchers at the University of Arizona says that an orbiting space mission could find out if there is life on Saturn's moon Enceladus. In the Planetary Science Journal, the researchers explain how a possible space mission could help find answers. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. Enceladus first appeared as a small, uninteresting snowball in Voyager 1 in 1980. NASA's Cassini spacecraft analyzed Saturn's rings and moons in detail from 2005 to 2017. Scientists were surprised when Cassini found that Enceladus's thick ice covers a huge, warm saltwater ocean that gives off methane. Cassini detected methane and other organic compounds in Enceladus' aqueous plumes. As the tiny moon goes around Saturn, friction from Saturn's gravity heats its inside. Enceladus fractures and crevices spew water plumes toward space. Scientists from the University of Arizona and the University Paris Sciences et Lettres decided last year that if life started on Enceladus, it might explain why the moon burps methane. To know if that is the case, we must go back to Enceladus and look, said Regis Ferrier, senior author of the new paper and associate professor in the Arizona Department of Ecology and Evolutionary Biology. Any life is probably microscopic. In their most recent paper, Ferrier and his colleagues say that even though the total number of living microbes in Enceladus ocean would be small, all it would take is a visit from a spacecraft in orbit to know for sure if Earth-like microbes live in the ocean under the moon's shell. Sending a robot crawling through ice cracks and deep diving down to the seafloor would not be easy, Ferrier said, explaining that more realistic missions have been designed that would use upgraded instruments to sample the plumes like Cassini did or even land on the moon's surface. By simulating the data that a more prepared and advanced orbiting spacecraft would gather from just the plumes alone, our team has now shown that this approach would be enough to confidently determine whether or not there is life within Enceladus ocean without actually having to probe the depths of the moon, he said. This is a thrilling perspective. Enceladus orbits Saturn once every 33 hours. The moon isn't as large as Arizona, but its surface shines like a frozen pond in the sun. At least 100 huge water jets erupt from the moon's south pole like lava from a volcano. Scientists believe these geyser-like phenomena contribute to one of Saturn's rings. Cassini sampled this ejected mixture from Enceladus ocean. Saturn's icy moon could support life, but we'd need to send a probe to be sure. Could Saturn's moon support life? Cassini's excess methane in the plumes recalls hydrothermal vents in Earth's oceans. At the boundaries of two adjacent tectonic plates, heated magma below the seafloor heats the ocean water through porous bedrock, forming white smokers. Without sunlight, organisms rely on chemical substances emitted by white smokers. On our planet, hydrothermal vents teem with life, big and small, despite the darkness and insane pressure, Ferrier said. The simplest living creatures there are microbes called methanogens that power themselves even in the absence of sunlight. They probably use methane as an energy source. Methanogens convert dihydrogen and CO2 to energy, generating methane. The calculations of Ferrier's team were based on the idea that Enceladus has methanogens that live in hydrothermal vents like those on Earth. Researchers figured out how many methanogens there were on Enceladus and if their cells and other organic molecules could be released in plumes. We were surprised to find that the hypothetical abundance of cells would only amount to the biomass of one single whale in Enceladus global ocean, said the paper's first author, Antonin Affolter, a postdoctoral research associate at Arizona, who was at Paris Sciences and Lettres when doing this research. Enceladus' biosphere may be very sparse. And yet our models indicate that it would be productive enough to feed the plumes with just enough organic molecules or cells to be picked up by instruments on board a future spacecraft, he added. Enceladus has gained attention as a place to revisit and study further. The Enceladus Orbolander, designed by the Johns Hopkins Applied Physics Laboratory, would arrive in an orbit around Enceladus starting in the 2050s. Our research shows that if a biosphere is present in Enceladus Ocean, signs of its existence could be picked up in plume material without the need to land or drill, said Affolter, but such a mission would require an orbiter to fly through the plume multiple times to collect lots of oceanic material. The possibility that actual cells could be found might be slim, Affolter said, because they would have to survive the outgassing process carrying them through the plumes from the deep ocean to the vacuum of space, quite a journey for a tiny cell. Instead, organic substances like amino acids could be used to prove or disprove the existence of a rich environment for life. Considering that according to the calculations, any life present on Enceladus would be extremely sparse, there still is a good chance that we'll never find enough organic molecules in the plumes to unambiguously conclude that it is there, Ferrier said. So, rather than focusing on how much is enough to prove that life is there, we asked, what is the maximum amount of organic material that could be present in the absence of life? According to the authors, if all measurements were to come back above a certain threshold, it could signal that life is a serious possibility. The definitive evidence of living cells caught on an alien world may remain elusive for generations, Affolter said. Until then, the fact that we can't rule out life's existence on Enceladus is probably the best we can do. Saturn's moon Enceladus is a top candidate in the search for extraterrestrial life in our solar system. Ecological thermodynamic modeling of the plume composition data collected by NASA's Cassini mission led to the hypothesis that a hydrogenotrophic methanogenic ecosystem might exist in the putative hydrothermal vents at Enceladus's seafloor. Here we extend this approach to quantify the ecosystem's expected biomass stock and production and evaluate its detectability from the collection of plume material. We find that although a hypothetical biosphere in Enceladus's ocean could be small, less than 10 tons of carbon, measurable amounts of cells and organics might enter the plume. However, it is critical that missions be designed to gain meaningful insights from a negative outcome, no detection. We show that in order to sample a cell from the plume with 95% confidence, greater than 0.1 milliliters of material needs to be collected. This would require material from more than 100 flybys through the plume or using a lander. We then consider amino acid abundance as an alternative signature and find that the absolute abundance of amino acids, such as glycine, could be very informative if a detection threshold of 1 × 10 to 7 moles L-1 could be achieved. Altogether, our findings set relatively high bars on sample volume and amino acid detection thresholds, but these goals seem within the reach of near-future missions. Initially, when NASA's Voyager 1 spacecraft surveyed Enceladus in 1980, it appeared to be just a small, unimpressive snowball in the sky. However, between 2005 to 2017, the Saturnian system was explored in unprecedented detail by NASA's Cassini probe. Scientists were amazed when Cassini uncovered that Enceladus' ice-covered exterior hid a warm, saltwater ocean that was releasing methane gas. On Earth, methane is often produced by microbial life, making Enceladus a fascinating subject for further investigation. The methane, along with other organic molecules that build the foundations of life, were detected when Cassini flew through giant water plumes erupting from the surface of Enceladus. As the tiny moon orbits the ring gas giant, it is being squeezed and tugged by Saturn's immense gravitational field, heating up its interior due to friction. As a result, spectacular plumes of water jet from cracks and crevices on Enceladus' icy surface into space.